My name is Aleksei. I'm with work for a company called Digital Magic.
I'm a software engineer there. The company specializes in Akka, Scala, and basically all things reactive. Today I'm gonna talk about Akka persistence. This is a framework that we've used in our recent project, and we're asked to share our experience with you, so that's what we're gladly gonna do. The talk is not gonna be only about Akka persistence, so I hope everybody would find something for them. So let's start. What is the problem that the framework aims to solve? Akka actors that Krista has talked about in the previous talk lose their internal state once they are restarted, simply because the state is kept in memory. So, simply put, Akka persistence enables these actors, for example, if you model an entity with an actor, to persist the state to a store more durable than memory, so that the state would be recovered once the system, and in particular the actors, get started again. So an example is if you model shopping carts with as stateful actors, then in case an application crashes and gets restarted, the user of the system would keep shopping as if nothing happened, meaning that the shopping cart actor state would get recovered. So prior to talking about the framework, let's talk of two actually theoretical things. One is event sourcing. Event sourcing is basically an approach in which you don't persist or save your current application state, not a snapshot of a state, but you save the changes that have led to the current state. So basically every change to your actor state or application state is recorded in a persistent store. It's called a journal. The journal is an append on the store. Events that are written there, or actually state changes, never get removed or overwritten, updated, or modified in any way. So the primary concepts of event sourcing are, first and foremost, the event. An event captures each change to a state, and it is an immutable fact, something that has already happened in the past. So here's an example of an event. One important thing to note is the name role has been added. The deed has already been done. For example, this user has been added the administrator role to. The next concept is the reconstruction of the state. So state is the current state of an application. Suppose you have started and need the current state, is reconstructed by replaying the journal, replaying all the events that were stored into the journal sequentially, and applying them to the state one after one. The application is done by a function that you provide. The function basically takes an old state event and produces the new state. And the function has to be deterministic, meaning that if it has once succeeded in applying an event, it has to succeed the next invocations. An example that everybody is familiar with is VCS, version control system. Once you make a change to your code base, this is captured as a commit. These commits are stored in an repository, And whenever you need to, for example, clone your code base into a new folder, you start off with an empty folder and gradually apply all the commits until you get the final version, the current version of the code base. And actually, event sourcing finds application in many real-world businesses as well. For example, doctors adding information to your medical profile. They don't scratch everything and erase everything. They add to the end of your profile. Or, for example, formal contracts. Whenever a change needs to be done to a contract, you don't strike things out, you release addendums to the contract. There are certain advantages to this event sourcing approach. The most prominent of which is that you have a complete log of every change made to the system or to its state for as long as the system has existed. And this gives a lot of business opportunities. For example, you have a system, you roll it out, a year later you understand that there's a new report that you're interested in, and the good thing is that you can get that report for the period that spans the entire system lifetime from the beginning, not from the day onward that the report was come up with. Another very important requirement that can be easily satisfied is auditing. You have every single change to the system captured as in a journal of events, so the only question is how you access it, but it's there. Event sourcing lends to good performance characteristics, meaning that you can choose a database specifically tailored for writes, for example, because the writes are append-only and they're not content for the same record. So, for example, you could choose Cassandra if you need. And another benefit is that issues, for example, in production, are pretty easily reproducible and debuggable. So for example, you stumble upon an issue, you take the event stream, the part of it that led to this problem, you take it out, replay it on the test system, and continue debugging from that point onward. And that part of the events, of the event log can be even made a test case setup, if you wish. But of course, there are drawbacks. One of the minor, from my opinion, ones is an increased storage capacity requirements, because naturally, if you keep all the data and never erase them, you will need to store them somewhere. But one might argue that this is a drawback at all, because one might think that data is value. So you might actually want to pay for this data to be available to you whenever you need it. Like I said, from the business perspective, business insight. But there's a serious drawback, is that it's troublesome to query data. So whenever you want to find me a user with name X, you start replaying all the events just to find out whether there was a user with name X. The event log is not easily queried, or it's very troublesome to query it. So to make this event sourcing practically applicable, another idea comes to the rescue. It's called CQRS, Command Query Responsibility Segregation, which is a very simple thing. It actually states that you can have different stores for reads and writes, and you might probably want to have them different, which I'll speak of on the next slide. But the idea is that if you cannot query the event store, the journal, which is depicted here, then what you need to do is just turn the events stored here into a representation that can be queried. So in this picture, the client issues commands which mutate state, and state mutations turn into events that get into the event store. That's it for the right side. Then, by some means, this is what Akka persistence deals with as well. The events get projected or streamed to the query store, which could be anything you like, and the client then uses the query model, which is totally different from the command model, to actually query data. The examples, the benefits of this idea is that, first and foremost, it enables event sourcing to be practically applicable, but the observation is that single data model, well, cannot be. It's, I guess it's a fact that it's very complex for a single model to be good at everything. For writes, reads, full text search, OLTP, access, if you want to access documents and stream your data, all these need a separate representation, a different representation. So the benefit of CQRS is that you can actually optimize writes and reads independently. You can choose a store for writes that's especially tailored for writes, and you could have as many stores for reading, for querying, as you have actually the requirements. Here I gave you some examples of what of potential queries that you might want to run. So another benefit is that reads can be scaled independently of writes. This means that if we observe a typical system, then writes are typically, I know there are exceptions, are being done a lot more, probably a couple of orders of magnitude less often than reads. So in a typical system, it's the reads that you need to scale, and scaling them up or having to scale them up with writes is a nuisance. With CQRS, you can have as many read stores as you like and scale them whenever each of them needs that. Of course, there's a drawback, which is also an increased storage capacity requirements. Not only for, if you go back, not only for the several stores representing the same data, for example, the event store holding data and query store holding the same data, but there can be many query stores, and as well as each store can have data in non-normal form. For example, if you deem it necessary to have a relational database as your query store, and you think that having data in non-normal form would improve the speed of your queries, then that is what you're that's what you're going to do, and that won't be a problem, because in the whole system, only the event store would be the single system of record. There would be no conflict in which of the parts of the non-normal form is the truth in case there's a conflict. So having considered those two theoretical things, let's move to Akka persistence. And Akka persistence is basically an implementation of those two concepts, the event sourcing and CQRS. Of course, it's built on top of Akka, and actually Akka persistence persists actor state, so not just any application. Here are some components listed, but please don't read them. I will cover them, or most of them, in the next slides. What's important to say is that two components are mentioned as experimental. This means that their API is not yet final and might change in the future. However, as of 2.4 Akka, the other ones are stable and considered production ready. So let's move to the first component. This is a persistent actor. You use it to persist an actor state if you model an entity with that actor. An entity is something that that you're familiar with. For example, it might be a GPA entity. This means that its state is persisted as it gets modified, and in case of an application crash, it gets recovered from this persistent store. Akka persistence deals with the following terms or concepts. There are commands. Commands are basically any Akka message sent to an actor saying, hey, please do this thing, which would probably result in state modification. Events are the same thing as in event sourcing. They capture state changes, and again, they hold the same properties. They are immutable facts of the past, and their application cannot fail due to this deterministic function, or its property of the function. And the state. The state is pretty much your plain vanilla actor state, but it's just modified by applying events to it. So in this picture, imagine there's an actor. Imagine the blue one is its state. A command comes in from an external entity saying, please grant administrator role to a user by this email. The system checks whether such a user exists. The system checks whether the acting user wishing to grant this role is actually an administrator, it's himself. And if all these checks pass, then an event is persisted, or the Akka framework is used to persist the event. The event says role has been added. This role to this user. This here is not has been added. This is an imperative sense grant event role. Whenever an event is added, the previous actor state, in which there's only one role user, the event is applied to the state by the means of this function that we've talked earlier to obtain the new state. As you can see, only the delta, the role that's been added, is applied. The next concept is event journal. Event journal is the same as in event sourcing. It's an event-only log. An important thing to notice is that each actor has exactly one journal. The journal is a stream of changes to an actor state. An actor state is quite private to it. It's not shared, as Chris had told us. So there's a one-to-one relationship between persistent actors and journals. This also means that you have to be careful for a cluster to have only a single writer to each journal. Otherwise, there's going to be trouble. The persist API is the mainstay of the probably the mainstay of the framework. It basically is all there is to this API. I'll walk you through it. You need to actually read it. So whenever you decide that the command has to lead to a state change, for example, in this example, a banking account has to withdraw some money from it, you create an event, balance changed, you tell the framework to persist it to disk, and once the framework persists the event to disk, it calls us back and says, hey, here's an event, I put it to disk. Now please modify your in-memory state. And this is the state application function invocation, which does this state modification. So using Akka persistence is quite simple in this sense. Snapshots. Snapshots are totally optional, but if you notice that your event log starts growing rather large, rather long, as a result of continuous state changes, then there's going to be one problem. This is recovery times. Whenever an application starts, you will have a lot of events to be replayed and applied sequentially in order to rebuild the current state. So snapshots could be used to record a snapshot of an application state at some point. For example, in this case, we started with an empty state. There were three events modifying the state. And then we decided that it is too long to recover it, this journal. We decided that a snapshot of a state, of the current state that captures all the three events, is to be written in a snapshot store. And events 4 and 5 get written after the snapshot. So it's important to understand that the snapshot is created of a single actor's state, not the whole system state. We talk about only the actor state. Naturally, there's a lot of community plugins to be selected from that implement snapshot stores. You can have it in file system, in MongoDB, Cassandra, relation database, whatever. And the same goes for the event journal. The events can also be written to a large selection of backends. Now here, I don't know if that's actually needed, but let me walk you through an actor startup. An actor starts up the same way, and a typical plain vanilla actor starts up. It's constructed, its state is set to initial, but then the framework may offer you a snapshot if there is one. For example, it may offer you this snapshot. And if a snapshot is offered, only these events will get replayed to obtain the state that captures all 5 events. If there's no snapshot, this empty state is going to be the starting state, and all 5 will be applied. So regardless of the existence of the snapshot, the final state would be the one that captures all 5 events. So this is to illustrate that snapshots are completely optional. And of course, while the actor is being restored, recovered, no new messages are sent to it, not to interrupt the process. This is the only slide with code in the whole presentation. I think having seen Akka interfaces is going to be, well, easy for you to understand it. This is the state of an application with one variable, balance. This is this application function of an event. If an event comes saying, hey, balance has changed, we change our balance by the amount we were instructed to. And there are 2 functions. Receive, recover. The function is called while the actor is being started. All the events are being fed to this function and are being applied to the state gradually. Once the recovery is complete, the receive command gets active, which is the normal functioning of the actor. It receives commands such as the one I've shown earlier. For example, if we receive a withdraw amount command, we first check if the state has such a amount of funds. If not, the command will not turn into an event. We're gonna reject it. Otherwise, we run that piece of code that I've shown you earlier. We persist the event and we apply the balance change event to our state. And that's all there is to a basic usage of Akka persistence. So persisting state is pretty much easy. The next thing is very important. It's the implementing side of the implementer of the query side of CQRS. So like I said, writing an event journal is good, but you want to query data. And you do that by exporting data to the representations in data stores that can actually serve those queries. And this stream projection, it's called a projection, is facilitated by Akka persistent queries. As you can see on this picture, there are two event stores, and this event store gets projected into two query stores. And also there's a read store to which two event stores get projected. So you can have data in your query store, that one, aggregate several event journals. Regardless of the fact that, for example, this actor event journal is being streamed to two query stores, the system of record is still this one. If this is buggy or fails, or this data gets corrupted for some reason, we could just drop the entire database and restream the entire history, because we have it, to rebuild this state. That actually can be used whenever you have not only fixed the bug, but have introduced a new query that you need to serve. That's pretty much goes hand in hand with the idea that Kafka uses. Another thing to note here is that the query stores are totally thought for the query that they're going to serve. If you need to query documents, use MongoDB. If you need to have some relations database like queries aggregating stuff from multiple entities, you could use a relation database. The simple idea of this persistence queries module is to have log transported to the event store. This one pretty boring and advanced topic, but it's more boring than advanced, but nonetheless, standard Akka, as Krista has told us, provides message delivery guarantees, which is at most once, and message ordering guarantees, which is peer-to-peer. So if I communicate with another actor, then he will see the messages in the same order that I've sent them. Akka persistence offers an improvement to this. The key point is that the protocol needs to have acknowledgements to your messages. So if I say, please receive a message, I expect an acknowledgement for you. And the key point is that each action, I have sent a message, and I, as a sender, have received a message, is persisted using Akka persistence. And for any messages that I have persistent, the fact that I've sent, it not informed the framework that I have acknowledged them, the framework will resend them during recovery. That's it, all there is to it. And of course, message ordering is no longer guaranteed because the dropped message gets retransmitted and will arrive out of band. There's a, well, if the receiver receives or processes messages in an idempotent manner, then this at least once message delivery actually becomes, or effectively becomes, exactly once. So no matter how many times I resend this message, if the result is the same, then this is exactly once delivery. Otherwise, of course, the receiving side has to expect and handle duplications. So that's basically it, what pertains to the framework. I would like to describe a use case that displays the use of this framework. The system is basically a user authorization and security policy management system. And being a security regulated environment, the requirement was that the changes to the state have to be audited. Any action that was done to the state has to be audited. An additional requirement was no relation database if possible. So how can we do this in a traditional way? We could still write the current state of the application into the relation database or whatever, resembling how GPA-based applications work, and teach our domain to actually publish events, publish the changes as events into some message queue or whatever. So every time the state gets changed, the code also publishes a message to the message queue. But this is problematic in the way that apart from you having several, actually two in this case, data models for read and write or for state and events, the biggest problem is that they may diverge. If these systems are different, you will have to implement two-phase commit to the both stores. If somebody ever forgets, after having added a write here, to publish an event here, this is the data stores also get diverged. So here's the architecture that we've actually used. I'll walk you through it. It is a cumulative picture of pretty much all the previous pictures. The client sends commands to a persistent vector that converts them to events and writes a journal. That's it, to the right side. Akka persistence is used to export the event log into an Elasticsearch publisher component, which publishes them to Elasticsearch. Elasticsearch is basically a distributed full-stack search engine. Now, the client wishes its queries served. There are two kinds of queries here, simple queries, but those requiring consistency. These go to the in-memory state of the actor. The actor itself serves the queries. And the audit queries, which tolerate eventual consistency, go to Kibana, and Elasticsearch serves them. One thing I forgot to mention previously is that this exporting takes time. Depends on the system, depends on the implementation, a couple of seconds, for example. So queries being done to the read store must be ready, must handle relaxed consistency. And probably the last thing to say is that this publisher is also a persistent vector by itself, so that it would know where it has stopped in this stream, so that after the whole system gets restarted, only the new events get transported to Elasticsearch, so that it wouldn't have to cope with repetitive updates. And the document IDs are based on event IDs, so these writes to Elasticsearch are basically exactly once, because the processing of the same IDs is idempotent on the Elasticsearch side. One last thing I would like to mention is performance. We have attempted to capture this information for you to understand what is the impact of the framework itself. And basically this means that we have done a few tests. If there is no persistence, nothing is written whatsoever to the event log, CPU usage is this, and network traffic is this, kilobytes per second. If we add persistence but do not snapshot anything, pretty much it remains the same. This is the traffic needed to transmit events. If we write snapshots really rarely, every 10K events, the CPU usage gets risen by somewhat, and network traffic keeps the same. But if we start writing snapshots pretty often, then this impacts network transmission. So this picture says one thing: the more snapshots you write, the the more resources you consume. But the persistence of events itself is pretty much free. But the next slide says that without snapshots, if the event log contains about 2 million records, the system starts in 5 minutes. If there are snapshots that are written every 10K events, pretty rarely, the recovery time drops to 30 seconds because the number of events is a lot less to roll. And of course, with frequent snapshots, it's even faster. So this is only to say that snapshots.
The logic of the last column there,
Logic of what?
Is that last right-hand column, if you say every 200 events, why do you have 12,000?
This one?
Yeah.
If we don't have any snapshots, then all events that there are in the system from the very beginning are replayed each time the application starts. And this is the number of those events.
Exactly. So with last line, you store a snapshot every 200 events, but then you still end up with 12,000.
Yeah, because there are many persistent actors.
Oh.
This is a statistic for the whole system, not for one actor. So to say it in words, snapshots cost you, but they also provide you reduced recovery times. So that's basically it. If you have any questions.
If you split state between actors and show that you project one log to two read models, read storages, for example, then maybe this read storages go out of sync if you ask them.
Like I said, one of the things to note in this command and query responsibility segregation pattern is consistency. The query inside should expect relaxed consistency. So if you are ready to tolerate, in our experience, it's a couple of seconds delay of propagation from here to here, then yeah, you can use this model. If not, you could, like I said, use this picture that we've also used. You could query the actor in-memory state directly, because these queries will be served in a consistent manner. This in-memory state gets updated by that apply function right after an event gets persisted into the journal. But of course, here you will have to write the
Logic to query.
well, not the logic to query, but the logic to satisfy the query. The engine to actually do the whatever joins or aggregation or whatever it is that you need from probably an off-the-shelf store.
And how many information can this in-memory state really maintain?
That depends.
Without garbage collector issues.
That purely depends on your architecture, because it's important to understand that Akka persistence is completely orthogonal. Well, it is orthogonal to the usage of Akka, and if you use Akka without persistence, you will be stumbled upon the same problem. If you see that an actor state is too big to fit into memory, you would have several options. You would rather have it on a dedicated computer and have all the other actors distributed among the other nodes of the cluster. If that is not enough, you could try sharding your actor. For example, if this actor is a user manager, this whole actor, then you could have 26 of them, each serving users starting with the first letter, right? So that really depends on the...
Then they will be inconsistent between each other.
Inconsistent between each other? In what way?
every will be different actors.
Yep.
So I can't rely on their current state if I need both users with one letter and second letter.
Like I said, it all depends on the architecture. If you find a way that's appropriate for you, for your particular case, good, and you can come here and present the solution. But what I want you to come away with is that the topic of this talk, the persistence, is not a solution to an architectural problem of, for example, how to design, how to model your domain with actors. And this is the question that you will have to ask designing that stage.
The journal or the event log, that is serialized to some disk file, or is that, how does that?
There are many topics that I haven't covered. Those include event serialization, data schema evolution, migration, persistent finite state machines.
Default is to serialize as events, or?
By default, Akka.
You use it.
By default, Java serialization is used. We use JSON for a number of reasons. Mainly because it's human readable, it tolerates small changes to the schema. For example, if a field gets deleted or added with a default value. And we also have this Elasticsearch thing, which accepts JSON. So it would be easier for us if we have just one serialization engine to fit into this and that database. But of course, you can have different serializers for each case.
And I think you're saving your logs into Cassandra, right?
Yeah, like it's written here, the event journal is in Cassandra.
And default is not.
What?
The default is level DB.
The default is not advised to be used in production, so I don't think it's reasonable to mention it. Yeah, it's in the file system or in the level DB.
Does each actor in this persistence model have some kind of an identity that survives? I mean, like.
Yes, you will have. This is called a persistence ID. It identifies the journal. So whenever an actor is started, if it is an instance of a persistence actor, then it has to provide a persistence ID. This persistence ID is checked with by the framework, and it finds the journal that is identified by this ID and streams the journal to this particular actor state. So you want this persistence ID to uniquely identify this persistent actor state. And that's why I also mentioned that the persistent actor has to be a singleton in the cluster if you have a cluster, because if there are going to be two different actors with different states writing to the same journal, the journal will get mixed up and you will kind of get data corruption.
But going back to the earlier, the previous talk, this cascade of governors, or what were they called?
Supervision strategy.
Supervisors and actors to. Are you as the programmer responsible for, like, to start up the whole thing again? Do you kind of restore each of your persistent actors, or there's something that takes care of the whole state as it was running?
Imagine there's no persistence at all. You have your actor system that in whatever sequence or whatever order you have programmed it starts creating actors. The very time an actor gets created, its journal gets restored. So Akka persistence doesn't decide which actors and when which journals and when to stream. You decided yourself by creating an actor explicitly.
Right, but I mean, like when you, so you had the system running, then it crashed, then you start up again, do you like kind of magically get your system restored, or you need to write that code to say, I will start up my persistent actors by these IDs that were like single IDs?
No, all you need to do is implement this persistent actor interface to provide a journal ID or persistence ID, and to implement these functions that will receive events which you as a persistence actor can apply to your state, and this function that will mutate state in the normal course of the actor's operation here.
So if I may add, maybe
So
the question is about Akka sharding, is that there is some system which will activate your persistent actors on restart, and basically boot them up. It
Right,
also
I mean,
will
somehow
actually,
you need to know the ID of the first persistent actor to restart, right? I mean, is that just a singleton, or do you need to keep that list in some other?
Well, actually, in our system, the actor that gets the master that starts, bootstraps the whole system isn't persistent at all.
So it must have a list of singletons then.
In our system, pretty much yes.
Okay.
That summarizes it, yeah. But of course, not every persistent actor is known beforehand, because, for example, there's a session manager which is persistent, and there are sessions that are also persistent. For example, if I, being a user of a web UI, I log in, I use the system crashes, gets restored, I keep being logged in. I don't perceive anything, that anything has happened. And this is what session persistence provides, which is not created at the system's bootstrap. It's created at the user login.
This very same example with a bank account, I would argue that this doesn't fit very well the Akka as an example, because the balance changed is a very good example of a thing that cannot be applied twice. I mean, you cannot replay it and have this at least once contract error. Because if you did in some did for some mistake apply twice, then your balance would be incorrect there.
But again, this function, or actually this function, is not called twice at any time, at any point of time. If this event has at some point of time in the past happened, then that means that you, being the system, have checked that it is allowed to happen, that all the prerequisites are in order, and you said, okay, now I give an order that this event is to be materialized and persisted and applied. So whenever the events get replayed, recovered during crash recovery, no commands ever happen. You just replay events that have already happened. It's pretty much the same as if we forfeit.
If an acknowledgement fails to come back, I mean, like you said, it gives you at least once guarantee, but it doesn't mean it cannot happen twice. If an acknowledgement fails to be received, so in that case you would have a mistake in your balance.
It doesn't give you that, because you will have to expressly use the framework to even achieve the even at least once guarantee. So I think what you're talking about lies in the domain of, again, of the architecture of the system, where persistence doesn't really make a difference. Because imagine your particular case, substitute Akka persistence to manually written persistence to some text file. Nothing should change from the perspective of your question.
so I think the question, if the command withdraw is sent twice or resent, then you will have problems, right? So you need a way to dedupe
it really doesn't matter. I mean, whether it's the command or the resulting event that balance changed -10.
So
So
the events,
if you fail to acknowledge the fact that balance changed -10, but you actually applied it to the state, which now the balance is -10, and if the sender then saw that it wasn't acknowledged, sends the same thing again, then the balance then changes yet again.
So your issue is deduplicating withdraw messages, right? So the originating actor who sends withdraw
This message
message.
gets lost. The message that says I have successfully withdrawn.
Yeah, but that happens after they apply.
Yeah, it can get lost in this very
Yeah, exactly. That's
very
that's the
approach.
position, right?
Yeah, but imagine this writing to a relation database. It's still there. So if you want this to be delivered in a guaranteed manner, you will have to facilitate that by yourself in both
Yeah, a lot
approaches.
more work to guarantee that it will happen.
Yeah, but in both approaches, with or without using Akka persistence.
So I think what you can do is you can add a counter sequence number to your withdraw commands, and you just deduplicate.
Then you would be building a relation database on your own, basically.
Not quite, more like distributed system.
We actually implemented such a system in our previous projects. It was complex, but it did help a lot. It did provide the sought-for delivery guarantees. But it's, of course, it's a matter of job.
That's essentially the transaction log, let's say, that Oracle is keeping. It's the same thing, basically.
So do you use two-phase commit with the message queue?
Well, you don't need a two-phase commit for that. I mean, you could still have it all in one data. I'm not arguing for a relation database, but it's just that there are situations like probably your security example where this is a much better example, whereas in a banking situation where you need to have consistency on the monetary values, then in that case, I think there is all those, let's say, reactive programs are usually either at least once or at most once, but they don't guarantee once. And so this doesn't fit with financial systems. And all of those big players that actually are doing all kinds of reactive stuff, whenever they get to the point where money is involved, they go to plain old relational databases.
And by the way,
because of this factor.
There's one other thing. In financial systems, you typically have a lot more writes than reads. So this is where the CQRS thing also doesn't work well or isn't that useful. So the purpose of this talk is not to convince you use this. It's to give you an overview that there is such an instrument, and whenever you see that your problem warrants the use of such an instrument, please go ahead. But if you see that this calls for another instrument, no problem, of course.
Well, I guess we have to thank our speaker unless there are more questions.